Okay, it is 5 p.m. in France. I believe we are live. So hello everyone, welcome to this webinar dedicated to immersion cooling and battery safety. I am Jean Chevalier, Exoes business developer. I am joined today by Exoes chief engineer Antoine Dubreuil, and we are glad to share the stage today with Dr. Cécile Perrat, CEO of OEMs. So maybe while people are still connecting, we can have a quick look at the summary for this presentation. Okay, early presentation, technical adjustment. Great. So first, Cécile will introduce the global context regarding the current state of battery safety and the concerns around thermal runaway topic. And then we will be focusing on how immersion cooling addresses these concerns, with first a short presentation of Exoes activity on immersion cooling, and finally some results from safety tests performed at Exoes on immersion cooled batteries. And we will end this webinar with a Q&A session. So if at any point during the presentation you do have a question, you can write it down in the Zoom chat. I believe there is a dedicated feature for that. And we will be addressing this question at the end. And also we will have a special guest for this last bit. So Arnaud Desrand, CEO and founder of Exoes, will join us to answer your questions. Okay, so I suggest we get started. And yes, Cécile, the floor is yours.
Thank you, Jean. So hi, everyone. Good morning, good afternoon. I'm Cécile. I'm going to go with you through this introduction where we are going to talk about battery fire, runaway, and thermal propagation. And we are going to see together if battery immersion cooling can help to reduce the risk of battery fire, and if yes, why. So I wanted to start my presentation with some facts, because we hear a lot of things about battery fire on the press. As you know, as soon as there is a battery fire, it's everywhere on LinkedIn. And I wanted to find data to start this discussion. What we can say is that Tesla, in their official report, says that they observe one fire for every 210 million miles traveled with their car. So to put this in comparison, the National Fire Protection Association in USA declares that they have one fire for each 19 million miles of vehicle. And this is all car you can see on the road in USA. So on this number, you can say that Tesla cars are much safer. I would like to put this in perspective, of course, because the statistic coming from the NFPA includes very old cars. So obviously they are less reliable. But all in all, in this data, we cannot say there is more EV fire, at least Tesla fire. And what I can tell you is that talking to any professional insurance company and many people, I have never seen anyone able to show me statistics showing that electric vehicles are more probable to go on fire than a normal passenger car. But what is sure is that when you talk to insurance people, they are very concerned about the damage that a battery fire can make. They are much more scary and much more dangerous for the infrastructure. So for example, a building, if you have a battery fire inside a house or inside a car park, it's so hot that you can start to melt the structure of the building and alter really getting a lot of damage. So even if we can say EV fires are not more probable than internal combustion engine, at least we can say they are more scary, and for the moment they are said to be slightly more dangerous. First, they involve new risks, so of course high voltage, but we can deal with this with the proper security. But in addition of this, they have also other problems. So they release a lot of toxic and flammable gases. And one of the main problems is that they are very difficult to extinguish. And we have data to explain you why. I will show that later in the presentation. But what is sure is that a fire on an electric vehicle can be very hard to extinguish, especially if people are not correctly trained. And another problem is that a battery, while it's extinguished, can reignite sometimes even hours later. So of course, All these problems have created a lot of discussion and concern at car manufacturer and end up to a lot of discussion to supplier. And I can tell you, I have not been in a single meeting for a year where we do not end up to talk about battery fire and security. So of course, it's very concerning for our industry. And because of this, we have many standards and there are many things to test when you develop an electric vehicle battery. And there are many tests involving security and safety for battery fire. The most famous one is the one coming from China, where they have 5-minute warning. So if you are not familiar, this is a regulation under which you need to be able to alert occupant on a car. And from the moment you give them this alert, they have 5 minutes to be able to escape the car. So it gives them the time to park the car and escape from the vehicle. It means that for car manufacturer, first, you need to be able to detect runaway as soon as possible, because otherwise you lose time. From this point, you need to alert passenger of the car, and you need to guarantee that during 5 minutes, and 5 minutes is short for people trying to escape, but long for engineer trying to delay a fire of a battery. So you have 5 minutes to guarantee that your battery pack will not get in a total fire. So you need to be able to contain any start of runaway and other problem inside the battery pack. And moreover, we are now expected, I have heard rumors that say that probably this limit of 5 minutes will even increase, probably from 2026. So it asks a lot of questions for car manufacturer. So as I say, among the development of batteries, there are many, many tests. And what is funny, if I can say, is that many of them will end up in a go-no-go about a battery fire. And even if tests that are not obviously talking about battery fire can end up in a battery fire if they fail. So for example, test on vibration, where you put cell, module, or pack and make them vibrating, can end up in terms of failure in a battery fire. The ones that you may know is the nail penetration. You see very often video of this, where you create mechanically a short circuit, and depending on the condition, you can end up to get a fire of the cell. And even things like immersion, on which you put the full battery pack in salted water for several hours, if you create a short circuit, can also end up in battery fire. So battery fire can be the one dramatic output, of course, of a lot of problems. So when you look what happened in terms of mechanism, I want to draw the attention that there are several different things. You have battery fire. You have runaway that will be defined as an increase of temperature, and you have thermal propagation. So runaway can be local or can be generalized, but thermal propagation will define the fact that maybe you have a cell that gets a problem, go and run away, and maybe you are not able to stop this cell to go on a runaway. But what you absolutely do not want is that the heat from this cell to contaminate, because it's too hot, to contaminate other cells and create thermal propagation, so other cells also to go on a runaway. So there exists method, and we are going to see together some of this in this webinar. About the mechanism of runaway, it's relatively complicated, and I could make a full presentation on 1 hour on this. But what you need to keep in mind here is that the timeline will depend on many things: chemistry of your cells, and also structure of your cell or design of battery pack. But in terms of temperature, we are talking here about relatively low temperature, if you compare that to internal combustion engine, of course. Because when you are already around 100 degrees Celsius, you are already quite in big trouble for going on a runaway trouble. And the way it works is that you have some chemistry that will release it because they have exothermic reaction. And the problem is that this chemistry reaction depends on the temperature. So the higher the temperature, the quicker this reaction to happen. So you will trigger a series of reactions that all of them getting exothermic, increase the heat and accelerate the process. And as the name suggests, go on a runaway. So it will involve mechanisms such as solid electrolyte interface decomposition, and it can make the separator of the battery cells melting, so you understand it's not a good idea to put in contact anode and cathode directly, or decomposition of the electrode, all of them releasing heat and ending up in a complete fire. So if we talk about battery fire, there are many things to say. And if you are on a traditional car, when you have a fire and firefighter put water on a car, it's not really the CP of the water that will stop the fire, but it's much more that the water you put evaporates, and this vapor stops the oxygen to arrive in the fire. So the fire will stop because it suffocates on the fact there is not enough oxygen. The problem is that you cannot do that on a battery pack, because the battery pack itself contains everything to burn. So it has already inside the cell the oxygen, because they are already stored inside the cathode material. So you can do whatever you want, the oxygen is here. Another thing to mention is the fact that the heat released by a battery fire is much higher than the energy you have stored electrically, because there are many things that can burn on the cells. You have also a lot of solvent, a lot of chemistry else that can burn. So it is a high level of heat release. And what is interesting is that if you consider the oxygen stored inside the battery, this is one of the main causes of this very big heat release. And if you can get rid of this oxygen, or at least stop the oxygen to be in contact with combustible to burn, then you will highly reduce this heat and be more able to control this fire. So if you want to stop a battery fire, you need to understand how it works. And of course, this equation is very simple, but you bear with me, you are going to understand what I want to say. So this fire is created from the fact that I told you the oxygen inside the battery will end up with organic material also inside the battery and make a combustion product and heat. If you want to stop a battery fire, you need to understand how the chemistry of this works. And don't worry, this is the only equation you will see in this whole webinar, but you are going to understand what I mean. So any combustion, would be battery or anything else, will follow an Arrhenius law. And you can define the reaction rate, which is related to the heat you are going to release, slightly a little bit also to the speed, but it's slightly different. But anyway, for the moment, we are talking about order of magnitude and physics. This reaction will depend on several things. So you have a constant here. Don't care about that, forget about it. But you have three things. The first one is the concentration of oxygen you have. So more oxygen means more heat release. Then you have the concentration of organic material, which is carbon-based. And again, more material to burn, more heat release. And you have an exponential with a constant. This is an energy of activation, and divided by a temperature. So if you can act on anything on this concentration, oxygen, organic material, or temperature, you are able to control slightly the heat release. What you can do, for example, is to say, okay, I want to get less oxygen. So this is possible, for example, if you change the chemistry of the cathode, because this oxygen is stored in the cathode, remember. So depending on the chemistry of the cathode, this oxygen will be more or less available, more or less stable embedded in the structure. And we know that already, because we know that, for example, LFP is much more safer than NCM, for example. If you cannot change the chemistry, another possibility is to say, okay, this oxygen is here, but I want to get this oxygen far away so it cannot be in contact with the rest. This is what you are going to do when you are venting system and security. This can be on the cell level, so you can expulse as much as you can the things far away. Or you also can do the same thing on the pack level when you have membrane and things that will make as much as possible gas going away. Another possibility is to say, okay, I want to put a firewall and try to stop this reaction to happen. So for example, there are things like separator on several cells that can melt down if the temperature starts to be too high. So first it gets, of course, the security that you stop the lithium going to continue. So if it's just a short circuit, you make a shutdown, but it also helps to separate a little bit oxygen availability to the organic material. And the last possibility, or there are other possibilities, but another possibility is to act on the temperature. So remember, we say we have things on the runaway and thermal propagation. If you cannot stop the runaway, maybe you can stop the thermal propagation. Maybe you can do that by putting donc separator between the cells. This is, for example, what is done when you use pad like aerogel between cells. Or another possibility is to use cooling system. And this is what we are going to achieve here, thanks to battery immersion cooling that Jean and Antoine are going to explain in the rest of this webinar.
And thank you very much, Cécile. So now, thanks to Cécile, we know more about the thermal runaway phenomenon and the upcoming challenges to improve battery safety. And now for the rest of the presentation, we will focus on how immersion cooling specifically is able to address these challenges. I will start with a short description behind the concept of immersion cooling, and more specifically battery immersion cooling. So it is a thermal management system that consists in cooling the battery cells directly thanks to a dielectric fluid. In the industry today, several architectures are considered for battery immersion cooling. And particularly in this presentation, we will be considering the specific architecture of full immersion with single phase fluid, which means that in this case, the battery module is completely filled with the electric fluid, and the fluid remains in its liquid state everywhere in the cooling loop. Okay. So the reason is that to date, it's the main architecture that we are working with today at Exoes. We have conducted projects on all 3 cell form factors, so pouch, cylindrical, and prismatic cells. And it is also compatible with cell-to-pack battery architectures. So this technology offers several advantages compared to the current indirect cooling method that is largely used today in EV batteries, namely the water glycol cold plate system. The first thing that I would like to mention is the cost. So in terms of raw materials, components, and system integration, the cost of battery immersion cooling is equivalent to the cold plate system. It is not more expensive, and actually it can even be more economical because the direct cooling allows to have smaller batteries with equal performances to the cold plate. And reducing the battery size obviously is very impactful on the weight and therefore on the price. Other benefits of immersion cooling is that it allows for ultra-fast charging, so charging from 20% to 80% state of charge in 10 minutes. It also enables longer battery lifetime, better performances overall. And today we are focusing on maybe the most important feature, its ability to prevent the thermal runaway propagation. Now, before we dive deeper into the technical part, I will add a few elements of context regarding Exoes activity for you to fully understand what we are going to show you next. So at Exoes, we work with OEMs and fluid manufacturers to develop this technology of immersion cooling and making it accessible to the mass market. Because the thing is today, you can already find some cars on the streets that have adopted immersion cooling, but mainly for the high performances advantages. And here we are talking about very expensive cars, hypercars, such as the Regera from Koenigsegg or the Speedtail from McLaren. And it is also the case in e-racing with Skoda, for example. So yeah, today, hypercars and Formula E are already using immersion cooling for the high performances it offers. And we believe that the mass market passenger car will also adopt immersion cooling for the high performances, of course, because it enables the fast charges, which is a critical point for the mass market today, but also for the safety reason. So at Exoes, we provide our partners with different kind of activities, starting with battery designs, so working with immersion cooling, obviously. And these designs are validated by different kind of correlated simulations. Then we perform physical test campaigns on prototypes that we manufacture as well in-house. So different kind of tests can be performed on these prototypes, such as a performance test, aging test, and the specific test performed to assess the safety of the prototype is called an abuse test. So an abuse test consists in triggering artificially a thermal runaway inside of a battery module in order to monitor the phenomenon and assess if and how it propagates to the other cells of the module, which is usually the cause of battery fires. And here there's something important to point out, and Cécile mentioned it earlier, but the difference between thermal runaway is that, so thermal runaway occurs inside of the cell, and it can happen for many different reasons that were mentioned by Cécile. And then we have the propagation of this phenomenon of the thermal runaway. And with immersion cooling, the purpose of the technology is to prevent the propagation in case of a runaway occurring in the battery. So it does not actually prevent the cell thermal runaway itself. And this is why during these abuse tests, we replicate the conditions for a thermal runaway to happen. Now a few words about the protocol that we apply for this kind of tests. So these are performed under very safe conditions. As you can imagine, we're basically exploding batteries. For example, the tests are performed on containerized test cells, okay? Oh, sorry, I missed this. No, this is right slide, sorry. These test chambers, we can mention that they are designed and assembled by Exoes. And regarding the actual test, so in order to trigger the cell thermal runaway inside of the tested module, there are several possibilities. And the method that we use at Exoes is either nail penetration or external heating pad. So nail penetration, Cécile mentioned it also earlier. The protocol is quite straightforward, actually. So it consists in running a nail into the cell. And this basically simulates an internal shortcut that triggers the thermal runaway. However, in more recent tests, we have been applying another protocol using external heating pad. So in this case, a thermal resistance is placed onto a cell, and it is then heated to very high temperature until it causes the cell to go into thermal runaway.
Sorry, Jean, to interrupt you, but it's something I have never seen before, this sort of testing. Is that something new, or is that something, what is the standard?
Yeah, right. Thank you for pointing this out. And indeed, this protocol, it's actually adapted from a recent standard, relatively recent standard. And the reason for this new standard was to define a more representative method to assess the safety of the batteries for automotive. Compared to the nail penetration, this method has, for example, better repeatability, and it is also less mechanically invasive, as you can imagine. So the drawback, however, is that this method requires additional consideration during the module design, because the addition of this heating pad inside of the module needs to be taken into account during the design. So with either method, the tested module is fully instrumented inside and out for a complete mapping of temperature and pressure at high frequency. Then thermal runaway is triggered remotely from outside of the test chamber, and the operators can monitor the test thanks to sensors and cameras. Now, the results that will be presented by Antoine in a moment, they have been generated by this kind of tests. They have been performed at Exoes. And here I would like to thank our partners that have accepted to share these valuable data with you today. So I will now pass on to Antoine for the presentation of these test results. Thank you.
Thank you very much, Jean, for the transition. So following up on the slide, and hello everyone. Following up on the slide introducing Exoes capabilities and our activities, we'll now take a look at 3 case studies that are covering all our development process for a robust and especially for a safe battery design. So naturally, we'll start from the beginning, what we call the model-based development phase, where we effectively develop safe modules through simulation and design. And especially in this case, where the target is absolute safety. So by absolute safety here, we mean no thermal runaway propagation, even in the absence of pumping power to actually circulate the fluid inside the module. So for the first case study, focusing on the simulation parts, I'd like to thank Dubreuil and echo what Jean was saying. as they've allowed us to share this data with you today. So that's from a 4.5 kilowatt hour module made of 12 pouch cells directly cooled in immersion. And that will be subject to abuse testing early 2023. So as part of the development process and the simulations we run to prove modules and battery packs for safety, we run what we call a thermal runaway simulation. So for this, we build a transient CHT model. So CHT means conjugate heat transfer, where we resolve both the fluid and the solid and their interaction together. And for this, we use a lumped capacitance approach, a lumped energy deposit approach. So here we initialize the system with the energy of a single cell thermal runaway event, and we let the system relax. We then monitor the temperatures of the neighboring cells against a set of defined criteria to determine if there is or if there is no propagation of thermal runaway. So in this case, for that particular study, we have demonstrated with good confidence that the final design is not going to propagate. The thermal runaway is not going to propagate across the module, and where the thermal mass of the entire module helps to effectively damp those peak temperatures sufficiently on the adjacent cells. So that's what's, and I will just grab the laser. That's what is illustrated on this graph that you can see on the left, where all the cells temperatures, so you can see that that's the cells group that are named other cells. You can see adjacent cells, so that's the evolution of temperature across time for the thermal runaway simulation. So the adjacent cells are the cells directly facing the cell triggered into thermal runaway. This cell number 7 is not shown on the graph, so it would be beyond effectively the limit of the graph. But what you can see is that very rapidly we see the other cells temperature that is increasing and effectively helps to absorb as much heat as possible to mitigate the peak temperatures on the adjacent cells. So this helps preventing the thermal runaway on these adjacent cells by limiting those peak temperatures. So a second type of assessment we do is the one you see on the right-hand side, for example, where we add an additional dimension, being the surface ratio beyond a certain temperature threshold. So it's effectively a plot of isosurfaces of temperatures, where we can assess, especially when we have some hot patches, hot spots on a cell, if they are big enough to be critical or to be of concern ahead of testing, effectively to understand the limitation of this design. Once this thermal runaway simulation is done, and actually in parallel, we also run a second set of simulation, this one specifically focusing on the venting. So here the focus is to understand what is happening during the first few seconds that precede a thermal runaway event, when in this case, for example, there will be more than 100 liters of gas that are going to be released in just a few seconds. So for this, we run a multi-phase CFD simulation using, for example, volume of fluid method, where the objective is to achieve optimal channeling of the venting gas. So this is supporting our design with a number of aspects, but effectively understanding pressure of distribution inside the module, understanding gas and fluid flow distribution as well inside the module, will help us to verify that the casing is strong enough, for example, with FE analysis as well. And consequently, will also help us to size devices like the burst disc or pressure relief valve that we could have on such modules. So this helps me to transition to the next step. Obviously, after simulation, we then typically at Exoes prototype and manufacture these modules in-house and bring them on our test benches. So I will present to you now a case study of a pouch cells module that was tested for safety on our benches quite recently. So it's a little bit of a smaller module. This one was tested using heating pad as the triggering method introduced by Jean. And we decided to run the test with active flow rate, but upon thermal runaway detection. So for this, we follow the ISO 6469 standards, which gives us a number of detection criteria that we can use to determine if there is or not a thermal runaway that's been triggered. So upon detection, pump flow will be activated. So we have already a plan to run also the same test without active cooling. This one will be in the coming weeks, but at least we can share these results today with you. Just to give you a better understanding of the test setup. So here you can see the module sitting on the bench. So it's painted in black for the thermal image recording. You can see piping, an exhaust line effectively that is connected to a burst disc or a pressure relief valve that feeds into an oil separator that effectively does exactly that, and then into a gas vent line that is connected to a filtration system. So we have also safety features like a spray nozzle, water spray nozzle. We have recording devices, so HD thermal cameras. You will see some extract later. And we have gas sampling for analysis, and obviously fluid sampling also included in the bench and test protocol. You can see on the right-hand side, an illustration of the heating pad that was used for testing. That was effectively inserted and mounted inside the casing. And you can see the hot patch surrounding the heating pad in the first few seconds of the test. So we'll now take a look at the result, and we thank Shell for allowing us to share these results with you today. So you will see in this graph, again, temperatures against time across the test. In blue, you will see the temperature measurements on the triggered cell. So different temperature profiles because we have multiple thermocouples on the cell. And in black, you see temperatures on the adjacent cell. So that's the cell directly facing the triggered cell. What you can see is that very quickly, in less than 30 seconds, we'd reached more than 400 degrees Celsius on the triggered cell. So the system automatically activated the pump and effectively was able to maintain the adjacent cell temperature below 50 degrees Celsius in this case. So this was a very safe test outcome and effectively a successful test in that sense, which concluded to no propagation of thermal runaway. Following up on the test, obviously inspection. So dismantling of the module, we can see 3 images here. So let's first take a look at the top right image, where you can see that we have located near what we called one of the side plate. So the heating pad was located inside that plate. You can see a certain amount of ashes that are located around that location. But when you look at the adjacent cell, so that's the cell directly facing the triggered cell, there was no visible damage, or at least no damage on the foil of the cells. There is a little bit of footprint from the testing, but no actual damage. However, when we look at the cell that was triggered into thermal runaway, we can see a very clear and large opening along the weld of the foils, which we understand is the location from where the venting gas were effectively expelled. After the visual inspection, we have the measurements. So we measure these cells for weight and swelling. And we can see that despite a 20% mass reduction from combustion, there was effectively no measurable impact on the other cells, any of the other cells. Let's move on to a different test setup, just to give you a comprehensive picture of, again, Exoes activities and capabilities. So here we've changed everything. It's a different form factor. We're looking at prismatic cells. It's a different triggering method. We're looking at null penetration. And it's different test protocol as we have no active cooling in this case. So you must be used now to the test bench setup, where you recognize the gas exhaust line that's connected to the filtration system. You can see the thermocouples and all the instrumentation that's coming off the front of the module, the nail that is going to puncture the first cell, and some of the electrical connection. We'll now get to a video, and we thank BP for allowing us to share that video and the data that will follow with you today. So we'll just get rid of the laser for a second. If I manage to do it.
I might be able to help you out by launching the video here, Antoine, maybe.
Thanks. Yeah. Just bear with us a second. We'll get there.
It looks like the video does not actually appear on the slide.
Okay. No worries. Oh, here we go. Okay, so before I hit play again, hopefully you can see what we see now, what we have on the screen. So you have on the right, and let me describe and prepare you a little bit for what you're going to see. So you have on the right-hand side an HD recording of the test, where you can recognize the bench, the module that is sitting on the bench. You can see on the left the nail that is going to enter into the module. You can recognize the exhaust line behind it. And on the left, you will have the thermal image recording that will effectively display the temperatures. So there will be a countdown. After the countdown and the nails enter into the module, I will ask you to pay attention to the top surface of the module where you will see a little bit of a pop. And following that, you will see temperatures raising effectively when the pressure relief valve has cracked open. So let's play again. You will see this countdown. So the nails goes into the module. And now you see the small pop. So you can see the exhaust line temperatures picking up. That's the gas hitting up the pipe. And you will start to see close to the front face a hot patch near the first cell that was triggered. It will give a few seconds for temperatures to evolve.
So, sorry again, Antoine, I have a question here. I think I'm not sure. You say this test is made with no active cooling, correct? What's the point to stop the active cooling here?
Yeah, thanks, Cecile. Effectively, that's a good point. So here we're trying to put ourselves in the worst possible case where we would have a double failure. So in addition to having a failing cell, which is going into thermal runaway, we also mimic the situation where we have a failing pump. So the coolant pump wouldn't be working. And we want to make sure that as a passive system, it is sufficient to prevent the propagation of thermal runaway. So here you can see that the temperatures have gone down below the 100 degrees Celsius mark, and they will continue to go down effectively towards a successful outcome, as there has been no propagation of thermal runaway in that case. So we'll move on now to the actual measurements, the result. So similar graph as before, you can see in blue the measurements on the punctured cell, which reached similar levels, so close to 400 degrees Celsius. And in black, the adjacent cells temperature, they were just under 105 degrees, so approximately 100 degrees peak temperatures, and effectively cooled down just thanks to free convection, effectively close to the triggered cell. So a successful test, which concluded to no propagation of thermal runaway, even in the absence of active pumping power to circulate the fluid. So now you're getting used to the process. After the test, obviously the analysis, so dismantling of the module, again, a certain amount of ashes when we look at the bottom image on the top of what we call the core pack, so the stack of cells. And when we look at the adjacent cell, so the top image, there was no visible impact on the adjacent cell, and the blue film remained intact. Now, regarding the measurements for weight and swelling, we saw about 15% mass loss from combustion on the triggered cell, on the punctured cell, but no measurable impact on any of the other cells. So that's it for the case studies, and because this wouldn't be a true webinar without a little bit of marketing to conclude, again, I wanted to bring you today some of the Exoes Group vision, as we have recently become Exoes Group, with a very strong focus on advanced energy solutions and not only thermal solutions, where effectively we are planning for 2027 to strengthen very much our Exoes Labs activity, which is most of what you have seen in this presentation today, which is planned to be home for about 250 people with very strong core R&D activities in the advanced engineering phase, and where we have the already existing and up and running immersive production branch, which we plan to have a 100% owned 1 gigawatt-hour production line in 2027. So that's about the future of Exoes Group. And I'll give you some numbers about the present and the past, just so you understand a little bit the extent of our activities. So as a group, we have run to date more than 38 immersion cooling projects with OEMs and fleet makers. We also add up to 150,000 hours of testing, which cover obviously safety, as we have seen today, but performance with a number of different, very demanding and stringent cycles, and durability with aging tests. We have 6 ongoing projects with major OEMs. So these will include 3 among the top 5, for example, but also 2 sports car OEM. And we have already validated and tested more than 7 designs. So by design, we mean here cooling architecture, cell form factors, for example. A few words just on immersive. So the production branch, which effectively develops submerged battery packs from A to Z, So effectively turning any kind of cells to modules or cell-to-pack architecture to deliver complete battery packs to its customers. So getting now to the word of the end. And before I thank you very much, obviously, for your attendance and for being so many to be still with us so far in the webinar. Just a few words again to come back on what we've discussed and what we've seen. We've seen that addressing battery safety, as was reminded by Cécile as well at the beginning of the presentation, that it is an absolute priority across the industry. It is the big word that we hear and that everyone is working on these days. We understand and we have seen that immersion cooling is a promising technology to really improve battery safety, and this allowing also all form factors to be addressed. We have seen pouch cells, prismatic cells today. A lot of Exoes experience is also on cylindrical cells. We have ongoing projects and some of our history on battery packs development for immersion on cylindrical cells as well. And we've seen that this can be done in a passive manner as well, where we have demonstrated that we can prevent thermal runaway propagation even in the absence of pumping power to circulate the fluid. So this was all about safety, but if you remember, or if you watch later the webinar from last year's, we've also seen and demonstrated that immersion cooling is capable of improving performance with ultra-fast charging capabilities and durability with extended life cycle. So I just want to finish this presentation with one of last year's headline, that we really believe immersion cooling has the DNA to become mainstream and mass market. So I'd like to thank you again very much, everyone, for your attention, for being still with us. And I guess we can dive into the Q&A.
Definitely. Thank you, Antoine. So this will conclude today's presentation. Now, as we move on to the Q&A session, I welcome Arnaud Derant to the discussion.
Hi, everyone.
You're with us. Hi. So, yeah, we have more than 50 questions. So thank you very much for your attention and curiosity. So we'll do our best, obviously, to answer as many as possible before the end of the session. And maybe starting up with first question. So what kind of dielectric fluid do we use for immersion cooling? Question for everyone around the table, but so basically I will take the lead responding to this. So today we are using different kind of dielectric fluid. Base oils are good candidates, obviously, and we are also studying some blends with different chemical blends, and esters are also good candidates, providing a differentiation on the durability. So these are all kind of candidates that we have been testing so far for immersion cooling.
I see we have an interesting question here that has raised some interest from the audience. A question from Andrew, asking what are the top 2 or 3 barriers that are preventing the widespread adoption of immersion so far, and what's possibly the timeline for solving them? Can you really answer that, Jean?
Well, this is something it's a very good question. Thank you, and I guess also we also have his words on this. But mainly, so far, immersion cooling have checked all the boxes of the requirements from OEMs, and it's climbing up the ladder of technology readiness level. I would say a barrier to this would be the reluctance from OEMs to change. Obviously, we have seen that taking risks for these big players is not too appealing when you have big car recalls that costs a lot of money. And this is why we exist at Exoes, to be able to test very thoroughly this technology for it to be accessible to the mass market.
I just would like to ask to add something. Is also, for the moment, I think on batteries, even if there are a lot of tests, there are not so many regulations if you compare that to traditional internal combustion engine.
Okay.
And requirements come from more tests and more things. As batteries are going to become more mature and they will end up with more tests and more safety and more security and maybe more things for fast charging and so on, then we will be in the need to push more technology. And I think here there will be a real opportunity for immersion cooling because of the evolution of the technology.
Yeah, thanks, Cécile. And if I may add, we are working hard to promote some standards and work with some other companies to create the future standards for battery immersion cooling testing, which is really important for us. But I want also to add that most of our customers, they have in mind start of production for mass market between 2026, 2027. So it will come really soon. And prior to that, sports car manufacturers, they have 2025 as a target for start of production. So this is coming, and we see every year we pass some milestones that are really important, like the design freeze, which we are not so far with some of our customers. And then we will launch the production together with them.
Thank you, Arnaud. Another interesting question. So with it, battery immersion cooling, do we have a dedicated loop for the battery cooling, or did we adapt every other components from the cooling loop? A very interesting question. Thank you for it. So indeed, today on the cooling loop is separated from the other components. The battery has a dedicated dielectric cooling loop, and it's actually a very interesting ongoing discussion on whether we can achieve to have one fluid for all, we call it. So this is definitely in the mind of everyone involved, and this will require additional analysis from different players, obviously.
Yeah, there are several questions that are exactly the same. What is the additional mass for this kind of system? And for mass market application, it will be exactly the same thing that water cold plate system, because we will remove the cold plate that is EV, and we will remove as well the heat shields and some other components, firewall between cells and etc. So if you add the pros and cons of each technology, we end with exactly the same mass for a given system with the same energy, and the feeding factors are quite the same.
There's something we can add to this also, comparing to the cold plate system, is that immersion cooling provides a better durability, a better recyclability, because today this thermal pad that is in interface between the cold plate and the module, well, it's very hard to dismantle and to recycle. So this is also a little advantages, but it adds up.
I also want to add the fact that if you want to go toward more safety, even if you consider other solutions like putting fin in between cells, for example, it adds also a lot of weight anyway. So we cannot get up to get more safety without making anyway more weight. So we need to compare that to other solutions that are also becoming more heavier.
Especially with tendency that is really heavy, is that the cell size is increasing. You know, we began with the 18650 for the cylindrical, then 21700. Now we are talking about 46XX new format, and this is the same for prismatic and pouch cells. They are becoming bigger and bigger. So the energy released when one cell is going into thermal runaway is quite high. And then you're right, Cécile, you need to add more and more stuff to avoid the thermal runaway propagation in the future battery packs, especially with new architectures like cell to pack or cell to chassis, where you have no module casing that's used to play, or that play the job of enabling no propagation between different modules. With future architecture and stringent regulation and battery safety, for sure, the need of new features will increase the weight of current technologies using cold plates. So immersion cooling will be probably even more effective in that sense, and probably will offer less weight in the future.
Thanks, Arnaud. And I think this answers one of the other questions that was raised, asking if it was possible to enable immersions in large modules or even at pack level. So yeah, I think the answer is yes, absolutely, according to what Arno just said.
So going back to the safety topic, how much volume of the electric fluid is needed to prevent propagation of thermal runaway? So actually, we don't need a lot of fluids to be able to prevent the thermal runaway, because being a direct cooling management system, it's very efficient, and we're able to dissipate very efficiently the heat from the thermal runaway of one cell. So the volume that we can maybe come up for the whole car with immersion cooling would be around 20 liters. So included the volume of liquid inside of the battery and also in the rest of the cooling loop for a typical passenger mass market car.
I have seen several questions about electronic and how you ensure that. A lot of people in the comment ask how you make sure electronic, BMS, and so on are separated or not from the cooling, how you make this.
Yeah, I can take this one. So there is obviously a significant amount of testing done, not only in battery, but compatibility of these fluids with power electronics, for example, which in some cases can be directly cooled. So these are things that we considered and that we are working on. And with respect to material compatibility, it's also something on which obviously also our customers and our partners, fluid manufacturers, have extended activities, and we also run dedicated activities on material compatibility to really understand and design solutions around that.
Right. Yes, so I see there are several questions that have been answered along the way. Also a question that was already answered, maybe from people joining in. I do have another one. What is the state of charge of the batteries that are ongoing the abuse test? The answer to that is 100% state of charge. Obviously, we are considering the worst case scenario and the one where we will have to deal with the highest amount of energy. Also, I see that our technical support answered a few practical questions. So I will address it right now. Indeed, if you want to retrieve the slide of this presentation or the complete recording of the session, please feel free to send a request to one of these contacts that you see on screen, and we will be very happy to provide it to you.
Regarding very specific question of what type of pumps we are using, what type of components, what is the space between the cells, etc. Some of the answers belong to our customers, so we will not be able to share this right now. You can intend to send us an email, and if we are authorized to answer this kind of questions, we will for sure answer this. But for this webinar, we'll take the general question, I would say, and general information on the battery immersion cooling and safety. And then afterwards, we will answer directly by email all those questions that won't be covered today. At least the one we can answer, and naturally, if they are protected by confidential agreements, we will tell you in the email as well.
I can see also in the question several that are the same related to recycle. Can we recycle the fluid? What happened in terms of recycling of the battery? What can we say about the recycling of immersion cooling?
So something we mentioned earlier is that it's a little bit easier to recycle a battery that has immersion cooling as a thermal management because it involves less energy in the disassembly of the battery. As for the coolant itself, so there are some candidates today that are being studied for immersion cooling application that are the esters. And they have this capability of being degradable. So the question being what degradable means today, this is basically the question that is currently being debated. yeah. Another one maybe for further thoughts. Do you intend to tackle air mobility market at some point in your development plan? So for the moment, we are very involved in the automotive markets, and there is a whole lot to be achieved. So technically, there is not any incompatibility with the air mobility, but we have learned from history that air mobility tends to observe what works in automotive and then is inspired by the best. So definitely something to keep an eye on. For the moment, automotive is definitely our main target.
I also can see a question asking if we can simulate fire propagation from cell to cell or only heat transfer. I will answer this one because I made simulation a lot in the past. Yes, you can simulate really advanced things. You can really simulate not only the heat transfer, you can make the venting, you can make also some detailed chemistry. There are many software that exist. In the simulations that Exoes shown here, they are already quite advanced, but there are many possibilities. You can nearly do everything with the simulation today. Not everything, but it's quite advanced. Of course, you can do that.
So I see in the question that we haven't answered yet, there are many questions that we have already addressed. So if you feel like your answer wasn't answered, maybe you can ask us for the recording of the session, and you'll probably find it somewhere in it.
I see one question that was just posted asking whether the dielectric fluid can also damage the cell. That's an interesting question. So, and which we also classify among the material compatibility activities. So we do run activities where we test fluids also under stability with, for example, electrolyte from cells, and making sure that there wouldn't be any issue if there was such a leak, for example, in the system. So that's also obviously an important aspect of the design, and that's considered.
And there are also several questions relative to the battery pack filling, the kind of volume, because we have liquid that needs to go around the cells, but the cells like prismatic or pouch cells needs to be compressed. So we do not take more volume than air cooling or water like cold plate cooling as of today, or this is really similar with our liquid immersion cooling design. So the question is not how do we feel more or less compared to existing solutions, because the ratio is roughly the same. However, we avoid thermal runaway propagation from one cell to the others, which is not possible with the other technologies. Okay, still 2 minutes to go, Jean. Still 1 or 2 questions before we close.
Definitely. Well, I would be very pleased to answer all of them. The thing is, we come back to the same questions. Okay, so maybe one more. What do you expect the module casing material to be? And what would be the expected pressure? So maybe expected pressure inside the module falls into the kind of data that we can't maybe share. But as for the material, Antoine, would you be able to elaborate on the material used for the module casing?
Yeah, I mean, as you've seen on some of the images, some of the material used for the prototype are metallic materials, for example, aluminum alloy. But we are also looking at different materials with requirements for weight, for example. We're looking at the next step to production as well, and that's together with the immersive branch on the production line, so there will be more stringent constraint on those aspects. But at base prototype level, to demonstrate the technology, we have the examples that you have seen, for example, in that presentation. Yeah.
Okay, and I will end this with the last question we just received. So are the fluid providers your partners? Do they buy a survey from you? So at Exoes, we have solely a customer to supplier relationship. We are independent, and this is also why we are involved in this in this domain, because we are trusted to have independent results for the OEM to assess with all the fluid manufacturers that we are in contact with. So this is how we operate, and we'll keep operating. So, okay, I think it's time to conclude this webinar. We're right on time. If you are still with us to this point, thank you very much for your attention. And again, feel free to reach out via the contacts that are mentioned on this slide. So we can provide you with, yes, the recording of the session or the slides or any other inquiry, really. So yeah, thank you, everyone, and goodbye. Thank you, Antoine. Thank you, Cécile. Thank you, Arnaud, for joining.
Thank you.
And don't forget to ask us any question we have not answered. We are on social media also, so find us here.
Yes.
Bye,
Thank
everyone.
you.
Bye.
Bye.
Bye, Owen.
Bye.